Otherwise, I will tell you something about magnetic systems. There is this confusion about what to call, I mean, which is free energy and so on. But before that, let me ask you if you have understood her. Disorder. Acha, entropy and disorder. Okay. Why entropy is a measure of disorder? Well, I think it is difficult to see it from the material that I have covered. So, there is a different interpretation of entropy in terms of that comes from the information theoretic background. So, that this just this S is suppose you have a set of configuration for which you know that the, so it is just, let me just see PC log PC. Okay, so, suppose you have a set of configuration C for which you know that the a priori probability is PC. So, then this is like another definition of entropy. You can check by putting PC equal to, let us say, constant for the canonical equilibrium, that you will recover P is equal to k log omega. So, there is a factor of k here, I think there is a factor of k, because this is dimensionless. So, there is a factor of, you can check that for the canonical ensemble, if you put PC is equal to e to the minus beta hc, you will recover the relation that relates entropy with the free energy. A is equal to u minus Ts. So, from this equation you will get for canonical equilibrium that S is indeed u minus A by T, because log PC will already give you Hc, and in canonical equilibrium u is defined to be this. So, one factor you already see, the other factor will also come. You want to have?
See, often people say entropy is a measure of disorder. That's not strictly true. I'll tell you one instance in which it's not. It's better to say entropy measures the number of available options. I mean, when you say k log omega, omega is the number of microstates which are equal, which have equal energies and therefore considered maximal, and that's all. Why am I making this distinction? Because there are examples of what are called entropy-driven phase transitions to ordered states. Entropy can promote order sometimes. Simple example, you have a collection of needles, hardcore objects which cannot overlap. Then if you increase the density, there is a transition from a state with the needles pointing in all directions to one in which they primarily in one direction. Certainly a phase transition from disorder to order. So what happened? Why? Because you are cutting down on orientational options. The reason it happens is by aligning. Sorry,
you can sure, please.
This way, each needle which is sort of aligned has a lot of options to translate between channels. The number of options goes up. The number of these options has gone down, but that is more than compensated by this. So be careful when you say entropy is a measure of order, depends, you have to be a little cautious.
Yes, somehow see this is, if it is a, maybe one way to put it, I mean the way I understand is, for an isolated system we have seen that the equilibrium state is the state of maximum entropy. Maximum entropy means gamma has increased, because AC is proportional to gamma, log gamma. So, that is proportional to gamma. So, somehow the number of possibilities has increased by this way. So, that is maybe a better way of putting it than to say that. So, in that sense they say the options has increased, therefore, it is not like ordered just one possibility, you have 15,000 possibility. So, in that sense that it is a measure of disorder, I mean so it is not really that you can measure disorder by, I just measure the entropy and that is the disorder of the system. There will be an exactly, there will be an order parameter. Yes, exactly. Yeah, it is the way in which phase transition is classified in the Landau sense. So there is something called an order parameter that appears. I think this is the context where it appears for the first time. You do a Landau, you write down a phenomenological theory that shows that the system will show phase transition, and this order parameter appears in that expression. It has of course this property that it will be non-zero in the ordered phase, and doesn't have to be really 0. I mean, you can make it 0. I mean, you can check another.
I just wanted to so the point is that for any phase transition, there are two sides. One is ordered side, one is disordered side. It's a general game. So, for example, water, ice to water, we call water in disorder, ice in order. But water to gas, we call it water in order, gas in order. I mean, something can be order or disorder depending on what kind. So, in every phase transition, a generic name is one side order, one side disorder.
Well, I think you have different like order parameters. You look at the difference of densities between solid and liquid and gas. So then, if you take these two definitions, then of course, this definition applies to this one, and therefore it is 0 here and non-zero there, and so. Yes. Anything else? Like if not, then maybe I just tell you or emphasize the main points of about the three ensembles. And so the first ensemble is, I think it's good to, this is my feeling, that it's always good to have a basic training in dynamical systems. The dynamical systems allows you to set up the equations. You have dynamical degrees of freedom, there is a function, this vector field that is telling you how the points are going to move around in phase space. And I think, phase space, if you look at it from that perspective, there is a Hamiltonian equations of motion. It could be, if it's a Hamiltonian system, it is necessarily a conservative system. Then, you may have, when you have integrability, it is easy to see what it means to be ergodic, that you have this phase space which is an n-dimensional torus, and therefore it is obvious that you will come back arbitrarily close to any point in the phase space, because the trajectory is going to reside on this torus. And that picture, I somehow feel that somehow that part is not taught in like MSc curriculum. I think it is not more difficult or more simple than anything else that you come across in. It is definitely simpler than quantum mechanics in the sense that you can at least visualize or play with a donut or a, which one is it? Vada. So at least you have some. Okay, so let me kind of so one way to do it is probably, so let me give you an overview of what I have been talking about and how did it lead to statistical mechanics. So the general setting that I was dealing with was that of n dynamical variables. For a Hamiltonian system, n is necessarily an even number, half of them are generalized coordinates and the other half are the conjugate momenta, but that's a special case. As we have seen, a dynamical system is defined by a set of n differential equations of this form, that and a nonlinear so these functions may depend explicitly on time, but you can make the system if the functions depend explicitly on time, then it is referred to as a non-autonomous dynamical system, but you can make a non-autonomous dynamical system into an autonomous one by increasing the number of variables by 1. So you introduce another dynamical variable which is called time, and therefore it has this obvious equation that the time derivative of the time is 1. So in the setting of autonomous dynamical system, there can be two broad class of systems. One is conservative and one is dissipative, and dissipative systems are those in which in the phase space. By the way, so before I go to dissipative system, we introduce this notion of phase space, which is very simply a space, an n-dimensional space. It has the same dimension as the number of dynamical variables. It's a space whose axes are the dynamical variables themselves, x1, x2, x3, x4, etc. up to xn, and therefore a state of the system is represented by a point in this n dimensional phase space, which is called sometimes it is called a representative point, or some books refer to it as a phase point, a phase space point, I think that's it. And then since these equations of motion are given to me, first of all the functions fi's, they themselves define a vector field, in the sense that they tell you where they, first of all what you can do is that given this set of fi's, you can draw a vector at every point in this phase space. So that will tell you, if you start from one point, where are you going to get to at the next instant. So these are the vector fields, and the actual phase space trajectory is the sequence of points that the sequence of phase space points that the system is going to visit as time goes by, according to this equation of motion. And therefore by definition a phase space trajectory is one in which if I draw a tangent at every point, the tangent is given, this fi's give the tangent at every location. You can think of it in one dimension. One dimension is kind of trivial because the tangent is just it can point only along this direction, doesn't have the other degree of freedom.
The velocity.
Yeah, so it's good to call it vector field instead of velocity, because somehow velocity, one might think that these are x's have to be length and so on. They need not be. They could be momentum, angle, whatever, concentration of rum in Coca-Cola, the example that we keep referring to. It could be anything. It doesn't have. So it's good to say vector field. And then we have seen the two broad class of dynamical systems, dissipative and conservative dynamical systems. So in conservative dynamical systems, what happens is that in this n dimensional phase space, if you start with a small volume element, then as time goes by, this volume element, the shape may get distorted, it may get like elongated and stretched and so on, but the total volume remains constant in time. Okay. It's not an integral of motion, but it's just that it's a constant in time. While for a dissipative system, what happens is that the shape, the volume decreases. That's why it is called dissipative. I mean, there must be something that is dissipating the energy of the system or something. So the shape continuously decreases as a function of time. So conservative, dissipative, phase space, and then we looked at some examples of one dimensional flows. So these equations, there will be some flow in the phase space according to these equations. Flow meaning simply that if I start from an initial condition, this initial condition is going to trace out a trajectory in the phase space. And of course there are some simple properties of these trajectories that we have discussed, that since these are first order differential equations, you cannot do like this. This is not allowed, because then the future is not defined, it cannot happen. Or if you start with two different phase space points, like initial points, then also the trajectories cannot cross. Okay. So this is just a reflection of the fact that you are dealing with first order differential equations. So in time, so once the initial condition is given to you, the subsequent future or the subsequent phase space points in time are determined once and for all. Then what did we discuss? Dissipative, conservative. Then we looked at some one dimensional flows. Okay, I did not have time to talk about two dimensional flows, and in two dimension you get a large number of like other motion. For example, you may have a spiral of this sort. Okay, this of course, can somebody tell me? So such a thing, let's say my axis, so this is a two dimensional axis, some x and some y, or if you prefer x1 and x2. So you start out somewhere you start somewhere on the outside, but then as time goes in, you tend to get into some point in this. It doesn't have to be zero. Can somebody tell me, like, is it a dissipative system or a conservative system? Conservative dynamical system or a dissipative dynamical system? Huh? dissipative, right? It is obvious that a large number of trajectories, they are all going to get to the single point, and this is called a spiral. So this is a spiral, and this is a stable spiral in the sense that wherever you start out from, you are eventually get into that. There is another possibility where you do this and you go out. This is not so common, but this is more common in dissipative systems. I mean, this I don't know of any example where such a thing happens, and there has to be some supply of energy or something. So this is very uncommon. Then you may have saddle node. So what you may have is a situation where so what you may have is, you may have a point which is stable when you move along this direction, which is unstable if you move along that direction. So these are unstable directions and these are stable directions, and a typical flow would be like this. And the way you analyze such a situation is, you first have to locate the fixed points. The fixed points are given by the solution of these equations, fi xi equal to 0 for all I. So you have to somehow get them, and in one dimension it's trivial. You have to draw the function and see where the function is passing through the x axis. Where is the dot? No, this is x and y. So the system is just this one, f of x y, y is equal to g of x y. Instead of writing x1, x2, I just wrote x and y. Sorry, x2. Yeah, but these are, when I am drawing the phase space, I should be drawing in xy plane. Okay, so this is one possibility.
So one question. So I mean, in 2D, you can also have cases where you go from one fixed point back and forth to another, right?
Yeah. So what may happen is that this we discussed in 1D. In 2D, I did not have time to talk about it. So these equations themselves may depend on a number of dynamical variables, and as you tune those dynamical variables, it may so happen that a fixed point which was stable became unstable, and so on. So these are not phase transitions; these are known as bifurcations, and the distinction between the two is kind of subtle. I mean, one must remember here, what one is interested in is the behavior of a given initial condition under the dynamical evolution. There is no notion of, I mean, those you know phase transitions and so on, there is no notion of free energy, probability distribution, peaked around some values, peaked around some other values, nothing like that. I have a set of coupled differential equations. I start with some typical initial condition, and I see that as I tune those parameters, I have different behavior of the solutions. So we looked at bifurcation in 1D, and we showed that there can be only three like elementary types of bifurcation in 1D. One was this, so the first one is the saddle node bifurcation, where you have two fixed points, one stable, one unstable, and then they meet at the bifurcation point and they like annihilate. So these are, so saddle node bifurcation occurs in those systems for which, for some parameter values, the dynamics may not have any fixed point. Okay. So this is the typical situation. Then there is the transclinic bifurcation, where you have a stable and an unstable fixed point, and when they meet, they just exchange their roles. Stable becomes unstable and unstable becomes stable. And the last one is the pitchfork bifurcation, where you have two fixed points, stable fixed points, they meet and they become friends and become just one fixed point. And
What, I mean, to change the parameter when you meet,
huh.
after that, you decide which one was what?
You can look at the stability, you do the linearization, you find out how do the, yeah, it's not that, so you have some equation, you have to look at it for some value.
To identify something was stable,
Huh.
this was unstable. When they meet, they merge. So after that, that's a new thing. How do
Huh.
you know that this point was the previous? How do you?
No, because you have one underlying equation, and what you have to do is that you have to do the stability analysis again, as he said. Huh? Yeah, when I'm not saying that they have these fixed points appear at the same values. Okay, I'm not saying that. It's not that. So it's in that mind that you have two fixed points. It's not that they are coming together in physical space. Not like that. This is a way to. These are not particles which are coming and hitting each other. In the parameter space, in the R space, basically as you tune R, they come close together, they merge, and then there's just one fixed point. Then I told you that in 1D flows, you can have only these three types of bifurcation, and the way to see it is what you have to do is that you have to first locate the fixed point, and if there is a bifurcation, you go very close to the fixed point, you do Taylor expansion, keep the leading order terms, and you find that in 1D only three possibilities are there. Like everything else, when you are close to the bifurcation point, it will reduce to one of the three. For the 2D, of course, I did not do anything regarding stability, but the way to go about doing it is you have to first locate the fixed points, go very close to it, do a linearization, and look at the spectrum, the eigenvalue spectrum of the linearized matrix. And it may so happen that you have eigenvalues which are both, so for example, if you have eigenvalues which are both purely like imaginary, so typically you have a situation like this. This is what happens in simple harmonic oscillator. No, this is not a limit cycle. So simple harmonic oscillator, you have this, that you just go round and round along one orbit. Or you may have a situation where there is one eigenvalue with a real part which is positive and another eigenvalue with a real part which is negative. And these are, by the way, the eigen directions, the straight lines that I have drawn. They will not be straight lines far from the fixed point, but very close to the fixed point, they will be straight lines because I am linearizing. So, I have just considering linear dynamics, and so this is the direction in which you have an eigenvalue with a negative real part, and therefore, whatever perturbations you make, they will decrease, they will decay in time, and this is a direction which is the growing direction, and so they will just go away. This you can read about it in Strogatz's book. It's nicely explained there. I mean, there's no so like everything can be studied in terms of just two parameters. One is the trace of this linearized matrix, and the other is the determinant, because I have just two eigenvalues. So I have two equations. One gives the the sum of the eigenvalues and the product of the eigenvalue. One gives the determinant, and the other is the trace. Which one is what? And okay, so for in this case, I also talked about limit cycle. At least give you some idea of. So limit cycle is when you have sustained oscillations with a frequency and an amplitude that doesn't depend on the initial condition. Whatever initial condition you start out from, eventually the system starts oscillating with a characteristic frequency and an amplitude. And surely a simple harmonic oscillator is not one such a system, because for a simple harmonic oscillator, obviously the frequency is given to you, that is how you define the oscillator, but the amplitude with which you oscillate depends on the initial energy. If the energy is higher, though, like obviously you oscillate with a larger amplitude than if you start the system with a smaller value of the energy. But then you can have situations in which in this n dimensional phase space you have an isolated periodic orbit, and we have already discussed that an isolated periodic orbit is not self intersecting. So, this is allowed, it just goes round and round. You may have a situation in this n dimensional space where you have an isolated periodic orbit such that wherever you start out from, you eventually asymptotically approach this one, or if you start out somewhere here, you eventually approach that one. So, that is the example of a limit cycle. It is an isolated orbit, as opposed to simple harmonic oscillators, where you have an infinite number of concentric circles, or typically you have ellipse, you don't have circle, you have a circle. And by the way, can one relate this to the torus example that I was talking about? It is that example. No, I'll come to that, but this is exactly for an integrable system, the invariant tori that I was talking, one inside the other, and so on. It's just a two-dimensional case, trivial case. Okay, so for this limit cycle case, which of course appears only in a two-dimensional plane, two-dimensional flow. For one-dimensional flow, we have seen that you cannot have oscillations. You cannot go back and forth. Either you go this way or you go that way. This limit cycle, there is a different kind of bifurcation that happens, which goes under the name of Hopf bifurcation. Hopf bifurcation. It has again a standard form, and I'll just tell you the the keywords. I mean, these are like easy to figure out. I mean, so the prototypical model is what is known as the Landau-Stewart oscillator. Landau-Stewart oscillator. It's a nonlinear oscillator, and this Landau-Stewart oscillator for some values of the frequencies will show this Hopf bifurcation. Okay, so and we discussed an example of this limit cycle, metronome, our heart, and like any oscillator that you see that has got a characteristic frequency of oscillation, independent of where you start out from. Like here, like even if I start from this point, eventually its long time dynamics is going to be dictated by this isolated orbit, and that has got a characteristic frequency and amplitude of oscillation. Similarly, if I start out somewhere here, eventually it will be okay. By the way, so I think Mustansir had a question, so I had forgotten to discuss it. Now I remember. Okay, so I think we discussed it in some length. In a two-dimensional flow, suppose you have an isolated orbit here, then we saw that if I start out somewhere outside, so these are my axes x and y. So this, the phase space trajectory, it cannot go inside because it's a two-dimensional plane, and this acts as a barrier. It cannot go inside. And similarly, if I start somewhere here, I may spiral in or I may asymptotically approach this one. For this thing, there is one possibility that it will asymptotically approach this limit cycle, or it just goes to infinity. So then the question is, do I call this a chaos, in the sense that if I start from two initial conditions, here and here, they are very, very close to one another, one just goes in, spirals in, and one goes out. So in that case, this will be a repelling limit cycle oscillator, that this, and this it just goes out. So it's a repelling limit cycle oscillator, unstable limit cycle oscillator. Or not. Do I call this a chaos? This I don't call a chaos, because here, although I am starting very far and very close to one another, and I am going very far, this is simply because the phase space is kind of unbounded. It's not that, it is chaos in a trivial sense. Trivial in the sense that it's not that you have a bounded phase space and yet two trajectories which start very close to one another are going very far apart. Yeah, it's a separate trick. So you can read about it in the case of pendulum. There is this libration and gyration. So these are the two possibilities. So one motion is like this, the other motion is like that, and there is a separate trick.
We have it in our sugarcane grinder. So whenever it slows down that ball, metal thing, that decides whether to continue rotating or to oscillate.
Oh, I see. Acha.
The two kinds of motion, whether to rotate further or to oscillate.
Acha. So this kind of situation, it may appear also in linear systems, that if you have a linear equation dx dt is equal to x, let's say, and you may go very far apart, like, which is, I would not call it a chaos, because it is like obvious divergence coming from the fact that your space is not bounded. So chaos is when you start with 2 points very close together, your phase space is bounded and yet you go very far apart. Okay, so a small like error that PK was mentioning in the specification of the initial condition. And the interesting thing about this error is that I do not call it an error, because whatever be the precision of whichever instrument you have employed to measure, to specify your initial condition, unless and until you have given an irrational number to your initial condition, it is always an approximation. You are anyways getting a rational number. A rational number itself is a truncation. An irrational number is one in which there is no pattern that repeats, and you have digits continuing all the way up to infinity. And like with any instrument that you use to specify your initial condition, there will be a truncation maybe at the 25th position or at the 78th position. Truncation by its very definition means that you do not know what is going, you are not giving information about what is happening beyond that. So in that sense, so whenever you see in dynamical systems book, you will come across this thing, a patch of initial conditions. I mean, you have this thing naturally in your system. You cannot really start with a given initial condition. This patch is always there. It's just a question of precision. You cannot have something with infinite precision. But anyway, so okay, so that was so we discussed these two-dimensional systems. Sorry, I did not have time to discuss these two-dimensional systems, but I told you what happens in 1D and this bifurcation picture. Then we jump to conservative systems. So these are systems in which a volume element has a volume that does not change as a function of time. And then I told you that in this a Hamiltonian system is a very good example of a conservative system, where indeed the energy is a constant of motion. And so for a conservative system, so n, the number of dynamical variables, is equal to 2n. So a conservative system necessarily has an even dimensional phase space, where n is the number of degrees of freedom. So please note that this is the number of degrees of freedom, not the number of particles. You have already taken into account all the constraints that were there in defining in some books they write somewhat confusingly that this is the number of particles, but it is not so. And conservative system is a very specific dynamical system in which instead of specifying n functions, you just specify one function, which is the Hamiltonian, and all the dynamical variables evolve in time according to some derivative of the Hamiltonian, either with respect to q or with respect to p. There is a very nice symplectic structure that it has. I mean, the conservative system, the Hamiltonian system is an example of what are known as gradient systems. So what is a gradient system? A gradient system has this structure, that it is the gradient of a function. So you just specify this function, just single function, and the different derivatives are going to tell you how the different x's evolve in time. And if you look at your Hamiltonian system, it almost has this structure, but not quite, in the sense that here if I write x1 dot, that is given by del x1 of fx. So it is 1 here, it is 1 there, and so on. But for a Hamiltonian system, it is kind of twisted, that if you want to know the derivatives of the q's, you have to take the derivative with respect to the p. If you want to know the derivative of the p, you have to derive with respect to the q. So it is kind of twisted, and that is can be expressed as what is known as a symplectic matrix. So it for a Hamiltonian system, you can define or you can write down the dynamical equations in terms of the following form. So there is a matrix so it is kind of the, how to write it. So this J is this matrix. So it is 0 I minus I 0, and you have the derivative with respect to the Hamiltonian. I have to put xt h x, something of this sort. So J is this matrix. What it does is that it mixes the Q's and P's, in the sense that if you want to know the derivative with respect to Q, the non-zero component is coming from the P part, and so on, with the right minus sign.
Is the definition of symplectic need 1 and minus 1, or it could be more?
No, this is the how it is defined. It's called symplectic because with this definition you can show quite easily. So a symplectic map, it is an example of a symplectic map, and one immediate consequence of a symplectic map is that as you look at the time evolution of of some volume element in the phase space, not just that the volume element is preserved in time, you take the projection of it on like any of the the planes, and you can consider 2 form or 4 form or 6 form, each of one of them is conserved in time. So I think I mentioned it, let me say it once more. So for a symplectic map, what happens is that, and a Hamiltonian system is an example of a symplectic map, that you have this some volume element in this n dimensional phase space, right, n dimensional, where n is 2n. What you can do is that you can take its shadow on the, let's say, the P1 plane, so it will give you some shadow. You can take its shadow on the P2 Q2 plane, P3 Q3, all possibilities. If you add the so this area of these shadows on each of the projected planes, that's going to be conserved in time. Okay, this is one possibility, where if you take the shadow on this 2-dimensional plane, you will get terms of this form. So here you will get terms of delta Qi wedge product delta Pi, sum over I, that's constant. You understand why you need to take a wedge product? Wedge product is just cross product in 2 dimension. So it's not a normal cross product in the sense that there is no vector. Cross product has to have a vector direction. So what is the wedge product? So if you take the projection of this volume element on one plane, you will get a parallelogram. And what is the area of a parallelogram? It's just the cross product mod. Okay, it's not the vector sense. So you take sum of all such projections, that's constant. So this is what is known as a 2 form, because you deal with 2 vectors. Okay, 2 form is conserved, 4 form is conserved, 6, 8 up to 2n. All these are conserved. So it's Hamiltonian dynamics is kind of very restrictive, very special. That not just that the full volume is conserved, its projections are also conserved. So that's the definition of a symplectic map. That it's a map in which you have to take no. You have to choose a pair of dynamical. Yes, the canonically conjugate. No, but so a Hamiltonian system is a very special. Yes, exactly, because exactly. So of course, a Hamiltonian system is special in the sense that for the Q's there is no negative sign, for the P's there is a negative sign, and then the equations are kind of twisted. That if you want to know the derivative of Q, you derive with respect to P, P derive with respect to Q with a minus sign. Everything equal footing, just as in the Hamiltonian dynamics. Yeah, there is conjugation, because I forgot to mention, and that's a good point to mention, that these Q's and P's are very special variables, in the sense that they are not just x's. The Poisson bracket of Q's and P's would have to equal delta Ij. So Q1 Q2 Poisson bracket is 0, P1 P2 Poisson bracket is 0, but Q1 P2 Poisson bracket is delta 1 2, and of course in the traditional way of doing things, setting up Hamiltonian system, you call Q is the canonical coordinates and P is the canonical transformation. Sorry, generalized coordinates and canonically conjugate momenta, but you can always do a canonical transformation to a different set where the Q's become the kind of the momenta and the P's become the. So, in that sense they are really on equal footing, but then the time evolution equations are not. I mean, this what you call momenta and what you call coordinate is kind of. Okay, so I talked about this the Hamiltonian system and then specialized to this very special class of Hamiltonian systems where there are integrals of motion sufficient number so that you can integrate the equations of motion completely. So, before that I think let us just it is just a recapitulation. So, I think no harm. So, what was our objective in nonlinear dynamics, and by the way nonlinear dynamics means that these functions are nonlinear functions, as simple as that. Somehow some people are intimidated by what's why is it nonlinear, and can you tell me one property which is strictly violated for a nonlinear system that makes all this all this field so different. I mean, one property which is exclusively satisfied by linear systems, you must have done it linear superposition, exactly. You have one solution, you have another solution, you just take the combination, that itself is a like another solution. You can take an infinite number of linear, but this is strictly violated in nonlinear systems. So, this automatically tells you that you may have many different types of solutions, different kinds of solutions. But there what was happening was, you see for the picture that I had drawn, well, these are the eigen directions. So, this is a linear system, I have gone very close to it, I have gone very close to a fixed point, these are the eigen directions, and I know how, let us say the flow is like this, that there is a stable direction, there is an unstable direction. Now, like even if I am not like moving along these eigen directions, I move along a general direction, but I know what the solution is going to be along a general direction, it is just a linear superposition of this and that. So, I will just get curves like this. I do not have to separately solve the equation, but such a system, such a thing is not going to work for nonlinear systems. And the aim of the nonlinear dynamical system theory, one of the objectives is to get this phase space trajectory right. I should be able to write down a closed form expression for the state of the system at an arbitrary time t given my initial condition. Okay. And then we argued that in order to do so, it suffices to find out, let us say this is my n is equal to 2n. So, I have n dynamical variables, capital N number of degrees of freedom. It suffices to find out or identify 2n minus 1 constants of motion independent, because for every constant of motion I know that this trajectory is going to lie on the corresponding hypersurface. So, then if I have 2n minus 1 independent constants of motion, then their mutual intersection is a one dimensional line, which is my trajectory. So, once I have done that, I am able to I can find out the trajectory in for arbitrary time. But now this very interesting and important theorem comes into play, which is the Arnold Louisville Arnold theorem, that says that for a system with for a system with n degrees of freedom, you do not have in order to integrate the equations completely, in order to find out the trajectory completely, you do not need so many constants of motion. It is enough to be able to identify n of them, half of them, and then I am done. And the way it goes is that what it says is that if you are able to identify capital N constants of motion, then you can always do a canonical transformation to this action angle variable, where the actions are constants, in the sense that in the transformed Hamiltonian, the angle variables, the coordinates appear as cyclic coordinates, and therefore, the corresponding momenta, which are the action variables, are constant in time. So, I have n constants, and n variables, the angle variables which are changing periodically as a function of time. And we have seen at least for one example of 2D harmonic oscillator, two harmonic oscillators coupled to one another, what's the trajectory going to look like. So, first of all, the motion will be confined to a 2-dimensional torus. If I have 2 degrees of freedom, if I have n degrees of freedom, it will be confined to an n-dimensional torus. Why it is a torus? Because you have n independent angle variables. So, for example, for a torus there are 2 independent directions for the angles to change. One is this the circle that comes, if you take a cross section, that is a circle, and the other one is this one. Now, you cannot do a continuous transformation to go from this to that. I mean, this is not possible. That is how a torus is defined. And your trajectory, your actual trajectory is going to live on this torus. That is because the actions are constant on this, they are integrals of motion, constants of motion on this torus. That is how you construct the torus. And then we have seen that what a typical trajectory looks like. If you start from an initial condition, what it is going to do is that it is going to wrap around the torus, and if the frequencies, the ratio of the various frequencies are rational numbers, then you end up with a closed trajectory, that you come back to your initial point and then you just continue moving. You have a closed orbit on the torus. While if the ratios of the frequencies are irrational, you do not come back to your initial point, but that is good news for statistical physics, because what it tells you is that although you do not come back to your initial point, if you wait long enough, this one point or this single patch, it is not really point, patch is going to densely cover the surface of the torus in the large time limit, and therefore you will have ergodicity. You will have ergodicity is by definition, what is when do I say a system is ergodic? In a given domain of the phase space. I mean, when you say ergodic, you have to say on which domain it is ergodic, and ergodic means that it has, the dynamics is such that it has come arbitrarily close to any point in the phase space. That is what happens here if the frequencies are irrational. If the frequencies are rational, it does not happen, but then we have argued that on the number axis, rational numbers are countable, they are you can count them. So, they have a Lebesgue measure, a measure which is 0. Typically, you do not get a rational number, typically you get an irrational number, and therefore, for an arbitrary initial condition, it is more likely that the frequencies are not in, the ratios of the frequencies are not rational, they are irrational, and therefore, you fill up the torus completely.
So, how many tori are there?
Infinite of them.
No, but what is the class of the infinity?
Yeah, I do not know how to characterize it. There must be a way to. So, the way it happens is that the whole phase space. No, I do not know if one can characterize. For example, for the harmonic oscillator. So, for the simple harmonic oscillator, these tori are these ellipses that you see. So, it is a system with 1 degree of freedom, 1 degree of freedom, and these are the tori. So, this is one, and the infinitesimally close to it there is another, and there is another, and so on. So, maybe there is a mathematical way of, but it is countably infinite, one of those, I mean. So, for an integrable system, your whole phase space is foliated by or laminated by these tori, one inside the other, and so on. And for a given initial condition, you are bound to lie on this torus or that and that, or so one of the infinite possibilities, and then you either cover up the whole the surface of the whole torus, then you say that the system is ergodic on the torus, or you do not cover up and then you do not have an ergodicity, but typically you will cover up, because rational numbers are very atypical, you will always have irrational numbers, and therefore. And I asked some of you to try this out, I mean, at least one, maybe you wanted to go to the lab, no? Maybe we can do that on one of these days. So, a very good, nice way to appreciate this rational versus irrational and this continuous curve is to do this CRO, play with cathode ray oscilloscope. So, on a cathode ray oscilloscope, of course, what you have to do is, what you do typically is, let us say for 2 harmonic oscillators, the phase space is 4 dimensional, but you take the projection on the Q1, Q2 plane as you were saying. And if you have a trajectory where, I rubbed it off. So, if you have a trajectory which is periodic on the torus, so what you will see on your cathode ray CRO screen is motion which is closed. Okay, it should not go out. And if on the torus the motion is aperiodic or quasi periodic, you will see some structure like this. If you wait long enough, you will see you just see some fuzzy this thing going on. And the fact that rational numbers are very atypical, it shows up very nicely, because you have to really fine tune. We all have some experience of how to get how difficult it is to get a closed curve on. By the way, these are Lysager's figures. How difficult it is to get a closed Lysager's figure on the screen, because you do slight perturbation. Once you get, you just go away from this thing. Then we talked about what happens if you add a little bit of perturbation to an integrable system. You have an integrable system to start out with, or put it differently, you have a system, non-integrable system, that you can look upon as a perturbation to an integrable system, and you ask what happens to this nice tori and so on. So, what happens is that the resonant tori they get destroyed. The ones for which the ratios of the frequencies are rational, they get destroyed almost immediately, because they are very fine tuned. The irrational tori do not get destroyed as soon as you make the system as soon as you make the system non-integrable. The ones that are less irrational are easier to get destroyed. So, they get destroyed like almost immediately, while the last one that gets destroyed is the one with the most, whose ratios of frequencies is the most irrational number, namely the golden mean, √5 minus 1 by 2. That is the most irrational number that you can. So, what you have to do is, so I know why it is called most irrational number, because you can write an expansion of this 1 plus 1 by 1 plus, yes, exactly, continued fractions. And then it turns out that for the square root of 5 minus 1 by 2, I think the convergence is slowest, I think. No, so.
I don't know, but I just know it's all in one order.
Yeah, yes, exactly. So, that is the most irrational, when you call a number most irrational or less irrational. So, the most irrational number is one in which no pattern ever repeats, like you have to wait infinite number of like infinite length beyond the, if you do a decimal expansion, you will not see a pattern that like ever repeats, and the most irrational number is that the period is infinity. Okay. Huh. Sorry? Sorry?
They are saying for any irrational, the pattern will not repeat.
No, so the less and more, they are in that sense that you may have some pattern that repeats. Huh?
No, but you can have a irrational number like 0.1, 2, 3, 4, 5, 6. Then, no, but it will not repeat exactly in a periodic way. So, a particular sequence might appear somewhere. So, question is, if you write directly, if you start writing numbers, somewhere 56 you will get, right? It's not that once you get 56, never in the sequence you get 56.
The most one is where you will never get it. That is very, if you think you can try it on the calculator maybe, or you will see that it is not, and square root of 5
maybe the desktop.
Huh? Maybe the desktop. Ah, okay, desktop will show all the digits. 16, 26 places. Yeah, so the most irrational is the one in which there is no repetition whatsoever.
No repetition of what?
Huh?
No repetition
Of any pattern, you will not be able to see. So, first of all, you have. There is no
For
for
56 you will surely find somewhere, right? If you with a small set, like in some number,
Hmm.
6 comes after 5.
Hmm.
Then somewhere or the other will happen, right? If you say that 6 never come after 5, and then 4 never come after 4, then you have limited thing. You cannot just go to infinity.
No, what I am saying is that I don't know. So, this is my definition, that you should not see a repetition of a pattern like
What is the
anywhere.
pattern?
Pattern is just a sequence, yeah.
But that is bound to happen if your pattern is of size 1.
Huh.
That will always happen.
No, not one. I mean, it cannot be just a single.
Then it will also do.
So, I don't know. So, it can be shown that the square root of 5 minus 1 by 2. So,
Something must not be.
yeah, something.
It can't be a binary sequence.
That's true.
So I think if you take a arbitrary sequence, I mean that can be a definition.
Hmm.
I'm just saying it bluntly. So I'm just saying that now if you take a length L somewhere,
Huh.
cut a portion of length L
Huh.
somewhere, and when L goes to L become large, you never find it anywhere.
How large? I mean, then that is not for any irrational. No, so I'm not.
No, for the CAM theorem, it is clear which are the ones that will be destroyed, and because they could put a condition on this m dot omega. So, where m is the vector formed by the integers and the omega are the frequencies. So, if the frequencies, if the ratios of the frequencies are rational numbers, so this is 0. Okay. So, if they are not rational, then this is non-zero, and what CAM theorem tells you is that those that satisfy a particular equality, a particular inequality, k epsilon by something, I forgot what the terms, they are going to be destroyed. See, this rational and irrational, there is
Whenever there is a repetition, you can express in the form of p by q.
No, it's not a full repetition. No, another definition could be that two, let us say, 56, average for any particular
it's not immediately obvious, and more than that, I tried to decipher this paper of CAM theorem. It's a very difficult theorem, very difficult to read, mostly because it is the proof uses concepts of number theory. It's not at all a proof in physics that you do with the only thing that I gathered is that they say that the numbers which are less irrational in whichever sense are kind of close to a rational number than numbers that are very irrational, and therefore, the ones which are close to a rational number are easier to destroy, and it can be shown the square root of 5 minus 1, the golden mean, is the most irrational number. So, that is the last one that gets destroyed as you jack up the integrability, non-integrability part of the Hamiltonian, the coefficient in that. Acha, the one that you mentioned. Okay, I was trying to read from Arnold and so on, so it's not it's not easy to read.
You have that reference?
Yeah, he. Yeah, so this perturbation theory, it is explained quite well in the book by Ott. They say why it is difficult to do the perturbation theory for the resonanto, right? The ones for which m dot omega is equal to 0, you end up with divergences. I think it is also explained in Goldstein, this classical perturbation theory. So, they what they did was they left out those resonantori and they looked at those tori which are not rational but not wildly irrational. And now I don't know what it means to be more irrational, and it really requires more than what I could. I don't think it is so difficult that we will not be able to understand, but I just did not have the time. I have to. But I think it is, before you jump to Cam theorem, but I think it is important to understand the importance of the, the novelty of just the Louisville Arnold theorem itself, that it says that, look, you have a system with n degrees of freedom. On the face of it, I mean, it looks as a surprise that it suffices to find n constants of motion. As soon as you have done that, it is guaranteed that a canonical transformation exists that could lead you to a canonically transformed system where the new Hamiltonian is a function of only the action and not of the angles, and therefore of course so trivially the system becomes integrable. I don't know actually, so let me give an honest answer, but so, and it is this part can be understood why the most irrational number to write.
That if the only now I'm just reading it. The definition says that when you write is a continued fraction, the convergence
Now I have to take in the
slowest.
so that's what I was saying, that the convergence is
Slowest. It will oscillate.
this 1 1 1 1 the
Just keep oscillating and the
slowest because we have just one.
so the first one is 1 by 1.
1 by 1 plus 1 by this one.
So the first one, if you take truncated 1 by 1, so this first one is 1, second one is 1 plus 1 by 1, which is 2, it becomes 2, it becomes 2, and then 1 plus 1, like if you do that, so that's the way you the first one is 1 by 1, second one is 2 by 1, 3 by 2, 5 by 3, 8 by 5, 30 by 8. Yeah, Fibonacci. It's just the consecutive rest of Fibonacci and the
Fibonacci. Okay, so much so for the this thing. Then we came to study. So we spent 2 lectures on thermodynamics, recalling the definitions of entropy and second. Or 2 lecture, 1 lecture. Sorry?
Can I ask a quick question?
Yeah.
I mean, I don't know the answer to this. So, suppose we talked about this integrable thing, and when you turn on a small equation, then there's the
Cam theorem, yeah.
Do you know, is there anything analogous in quantum systems, or that's a totally open question?
No, I don't know if there is.
Try to do the semi-classical, and then they end up with this.
No, for the quantum generalization, I don't know of any definitive statement. I mean, so for example, this Cam theorem is analytical. You can bound. For quantum, I don't know of any analogous result. No, analytical that I. So then we did. Okay. So also I talked about mixing. So let me come to that, and then I have half an hour for stat mix. So that's okay, right? Half for this. Okay. So then what was mixing? So ergodicity, we said that in the phase space, for an integrable system, the motion is ergodic only on this torus, not on the whole of the energy hypersurface. And that's kind of bad news for StatMech, because StatMech wants that the foundation is this postulate of equal a priori probability that the system is equally likely to be found anywhere on this energy hypersurface. But that's not what is happening for integrable system. But you may have a situation where integrability is completely lost. Well, I showed you this example of this. So Henon-Heil, Henon-Heil. It's not like again Heil's Heil Hamiltonian, where you can do this numerical experiments and see that the resonant tori, the invariant tori are getting destroyed one by one. And the next level of complexity, or the next situation that you may come across is, well, now that you no longer have this integrability and this nice structure, what may happen is that you may have ergodicity on the whole of the energy hypersurface. Given a dynamical system, it is not easy to show or demonstrate that the system is ergodic. In fact, for the classical situation, you had asked me to make a list of it. I should do that. It's actually there on Wikipedia, but I can bring the Sine Gordon model and all those. Toda lattice. So the next thing is you don't have integrability, but you may still have. You don't have integrability. You lose ergodicity, but there may be situations where you have ergodicity on the energy hypersurface. That is, start from any patch of initial condition, like any measurable set of initial condition. That's the word, right word to say. I mean, see, so whenever in dynamical system theory we say you start from an initial condition, start from a patch, and basically what we are doing is we are discussing the behavior of typical initial conditions. If you start with very atypical ones, then these theorem have nothing to say. You know, if very specially manufactured and engineered like initial conditions, they may behave in a very different manner, but typical initial conditions behave according to what I talked about. So you may have ergodicity, that is, this typical initial condition is going to visit everywhere on the, it's going to come arbitrarily close to any point on the phase space, and then what I can do is that if I have to do a time average, so one way to do it is I start from an initial condition, I evaluate my quantity of interest along the time trajectory, I let it go for a very long time, so that is my t equal to 0, I let it, I like evaluate it along the time trajectory for a long time, and I have a time average. And if the system is ergodic, then I know that in this very long time stretch, this single trajectory has visited all the possible phase space points, and therefore I can replace this time average by just one time snapshot. So what I can do is that at a long enough time, I can say I don't do time average, I just say, well, by this time the system must have visited all the points. So I assign some probability to different regions of the phase space, and I do just an average over the phase space distribution. Okay. And for statistical mechanics, you don't know beforehand how to make this assignment, that well, this region may, you may have visited this region more often than not. So typically what you do is take the safest route, which is to say that all regions are equally likely, and that is the postulate of equal a priori probability, based on which you derive some results, you go back, check with experiments whether your results match, and then you say that, well, this it must have been true, like otherwise how come a set of results derived on the basis of postulate of equal a priori probability are matching with experiments. So that's one complexity. The next complexity is when you have mixing. So what is mixing? Mixing just says that, well, you have your, we are still dealing with a conservative system. You start with a patch of initial condition, some volume element in it. The volume is going to remain constant in time, but the volume gets so wildly distorted that like eventually this same volume or the same amount of phase space that you had started out with is going to fill up every region of the phase space in the right proportion. Right proportion meaning that in like the density is the same uniform, it is uniform across the whole of the phase space. And the best example is the example, this rum and Coca-Cola, or the ink and water, that you take a glass of water, you put a drop of ink. So there is some density of ink which is concentrated at one point, and if you wait long enough, if you do some stirring and all, then you find that eventually you get to a state wherein every 1 centimeter cube of water you will find the same density of ink. So we say that it's a very well mixed cocktail or mocktail, so it's the same. The nice thing about this is that in the actual setting, also there is this, I use this rum and Coca-Cola because I mentioned this in the, there is a historical, so this thing was first, sorry?
YouTube knows.
YouTube knows, I have already done it, so they know that I am giving this example. So the story goes that Gibbs was the first person to introduce thing in a very Puritan way, giving the example of ink and water. And like over the years, many people have made important contributions, like Halmos and Kinchin and Kolmogorov, and each time they used a different example. So the most popular is rum and Coca-Cola, and so on. So there are other
That must be very new. Coca-Cola is new.
no. Like in America, it's very old, no?
More than 100 years. 1880. Oh, I did not see it for first.
But it was not there in India, maybe, no? It came. But anyways, the nice thing about this mixing is that in the actual rum Coca-Cola example, I mean, one has to do some stirring. I mean, you have but here the dynamics is itself doing this mixing. You don't need any external force or like anything drive to set up. And like obviously mixing implies ergodicity. If it is going to be in equal proportion in every volume element, so then of course the system is ergodic, but not the other way around. I mean, ergodicity is a weaker condition, mixing is, it's, and in mixing what you definitely need is, since you would want this small, drop of ink to go get to each and every corner of the glass, you would need that this initial volume element, while retaining its volume in time, gets distorted and, develops this kind of tentacles and like, this kind of features. You start from somewhere here, and then like eventually you become like that, okay. So it fills up every, so this necessarily implies that if you start from two initial conditions which are very close by, they eventually get very far apart, and that's what is leading to this drop off in getting to very remote parts of the phase space. And you may have power law separation, or you may have exponential separation. Power law separation, it's not usually referred to as a chaotic system. A chaotic is when you have the, as soon as you have prepared your initial condition, the fastest possible separation that you can think of, that's chaos, and that's when you start from two initial conditions which are infinitesimally close, and yet you have an exponential separation. In a finite time, you just go to very, very different parts of the phase space. And let me just emphasize once more that you have this divergence not because there is a lot of room in the phase space. I mean, the phase space is still bounded, yet you start from two initial points, one goes here and the other. For example, the picture that PK had, that like this V2, if you displace it slightly, so then it is going to first collide with second particle and then third, or like first with one first particle and third. Okay, so this. Okay, so then let's come to this statistical mechanics. So microcanonical ensemble was the first situation that we had considered. So that's a situation when you have a system which is completely isolated. And this is a Hamiltonian system, classical Hamiltonian system, dynamics governed by an underlying Hamilton equations. And if you, so for such a system you would draw the phase space, and then the phase space, the motion in the phase space is characterized by this phase space density rho of QPT. And you might get to a state where the phase space distribution doesn't change as a function of time, and that's what you call an equilibrium. Well, technically now that you have PK's lecture, it should be called a stationary state. I mean, equilibrium is a specific situation where not just in the phase space, not just that the distribution is changing, not changing as a function of time, you have an additional thing that you don't have a closed loop of current in the phase space. So if you consider some loop here of or let's say no net flow of current across a plane that you were saying in this phase space, and if the system obeys detail balance, then you can show that this current is identically zero. It's very important to remember that the current has to be identically zero. You may come up with a region of a phase space where the current is zero, there is no net flow, but there is another region where there is a flow. I will not call it, you will not call it, or no one will call it an equilibrium system. The current has to be identically zero across any plane that you can consider in this phase space. So rho is not changing. If rho doesn't change, we will call it a stationary state. Why we will call it a stationary state? Because of our very definition of a macroscopic observable. A macroscopic observable is defined to be the average of that observable like over this distribution rho PQT. Okay, so we had introduced this identification that so you have some quantity which is a function of the phase space observable QP, and there is some distribution associated with it QPT, and so this is what I measure in experiment. Because when I am doing an experiment, the macro state is given to me, the system has got this much volume and this is the temperature and this is the pressure, and just on the basis of this information there is no way to find out which specific microstate the system is in. So you say that, well, let me take account of all microstates but assign different probabilities to different microstates, and I know how to find this function in principle because it obeys this Louisville equation, del rho del t plus rho h Poisson bracket is equal to 0, and if rho is not changing as a function of time, O is also not changing as a function of time, and therefore if I measure something now and 1 hour later and 5 hours later, I will get the same value and I will say that the system is in a stationary state. Equilibrium is a subclass of stationary states where not just that the value is changing as a function, not changing as a function of time, there is no net flow across any plane.
Simultaneously occur because if there is net flow,
Huh.
then quantity will change.
Sorry?
If there is some net flow, suppose
Huh.
stationary state is there, but flow is there.
So it's a non-equilibrium stationary state.
But
No,
if the flow is there, then it is automatically non-equilibrium.
No. Flow, so you are saying that if there is a flow, it cannot be stationary.
No. I am not saying. I am saying that if the stationary state is there, and if the quantity is not changing, it must be equilibrium.
No, equilibrium means two conditions. So first of all, stationary state. Let's go to
Conditions are satisfied, only the quantity will remain constant.
no. Let's go to the definition of a stationary state. Stationary state, just on the basis of intuition, what we call a stationary state, a state for which, macroscopic observables have time independent values. This is the definition of a stationary state. That a macroscopic observable, not something that that relates to one particle, that is of course changing, but a macroscopic observable doesn't have a explicit, it doesn't have time dependence. So then I say it's a state to be a stationary state, and it just tells me that if the macroscopic observable is not changing as a function of time, that means rho is time independent.
My question, if it is stationary state but not equilibrium state, the macroscopic variable has to change.
If no, by definition a stationary state is one in which the macroscopic observable is not changing. See, I am not saying that there is no current, I am saying that there is no net current.
No, but is it possible that currents are there yet quantities are constant?
No, I don't think so. If there
If there are net currents, then quantity has to change.
no, that's not true. That cannot happen.
So maybe the example of heat conduction.
No, any conduction. For example, if you take a wire and you put some voltage, there will be a current. It's a definite current, right? It's not changing with time. There is some current. It's not changing. There is current, but the observable what you call current, that's not changing.
Acha, so there is a net flow, and the value of that net flow is unchanged in time. That is also not changing in time.
How you can realize this thing for the pressure volume like suppose you say the temperature is
But you can set up a temperature gradient, for example, right? So you can take something and put a high temperature here, low temperature there, and then after a long time, of course, the system would have a temperature profile. So
And therefore there will be a net current.
Just so the temperature, I'm just saying that if you take a wire and put some temperature.
No, I put a wire. I mean, you can do this thing also. What are our familiar example? See, here there is a current. So if I measure the current here, when do I call it a stationary state? So across this cross section, there is a net flow, and the value of that current is unchanged in time. So it's stationary, and there is a net flow.
flux divergence is zero like that. Yes.
No, but I'm giving another example. Not current. For example, if you take just this heat problem, it is 2, and then you from beginning put thermometer. Initially the thermometer will show something, but it will change and it will fix to some value after some time. Right? I mean, initially
Yeah, so like
one is above room temperature, one is below room temperature. Now everywhere you put a thermometer. Initially all the thermometers were reading room temperature, but some of them will go up now, some of them will go down, and after some time that will be steady.
yeah, this one. See, if you start with T1. Yes, exactly, exactly. So there has to be an extra. Okay, so that's what he. Okay, okay. There has to. It has to. See, such a closed system will not have a non-equilibrium stationary.
Think of it as an isolated system.
Then of course. This is so this one cannot have a net current. See this one.
So that will happen together. What is my stationary state and equilibrium will happen together with the isolated system.
Well, equilibrium is a stationary state. It's an equilibrium stationary state. You don't have a net flow. So stationary state can.
The question is, can a non-driven situation have a stationary?
See, drive doesn't have to be. Yeah, but there has to be some drive. It doesn't have to be a physical drive, but something has to be there. Or to put it differently, something has to be there that would have to break time reversal symmetry explicitly. For a closed system, Hamiltonian system. No, for
Basically, current would be 0, but it could be non-equilibrium because there are currents in phase space.
yes, exactly. For
In the isolated system, is it possible that stationary state is achieved, but it is not the equilibrium?
I can give an example. So question is that there are, let us say that this what you call system, there is a direction, the current there is direction. So let us call it left and right. Okay? So whenever a particle goes to left, a single particle can go to left, but whenever the particle goes to right, only two particles can go to right. Okay? Two together can go to right. In this situation, you can never have equilibrium because when you change the configuration by taking to right, it's only by one particle, and you cannot come back just like that. The configuration you cannot bring it back. You can have zero current or non-zero current still, but it's isolated and still it is going.
you see, for this one, I just.
Okay, I think with my examples I can sum.
No, for this one, let's come to this one. This is an isolated system described by an underlying Hamiltonian. This system will have only equilibrium stationary state. Hamiltonian dynamics, time reversal invariance, therefore you cannot have current. In his example, when you are saying isolated particles are moving, that means there is an external drive somehow. You are saying that particles are more likely to go this way than that way. So I would not call it an isolated in that sense.
No, it's only right side and left side, but it is possible that the two particles go to the left.
Okay, but still there is something that it's not isolated in that sense. Let's say for this one, let's look at it this way.
It can happen due to the initial condition. For example, you take like a slightly exotic thing like a superconductor, set up a current there, it'll just keep going on like this, right? So that's not an equilibrium thing, but it's a stationary thing, right?
But in this setting, you will not have any such thing. When you have an isolated system described by an underlying Hamiltonian, the Hamilton equations of motion are manifestly time reversal invariant, and therefore you cannot have a situation where you can say by just looking at the dynamics, by looking at the video that time is going this way, because this way is as likely as that way, and then there cannot be no net current in the phase space. That's important, that's more important than, so that's why I was drawing the picture in the phase space, that there is this example where there is no external drive, so to say. This what is this model? This Takahashi model. No, there is a current, but it's not current in the sense of ASEP and TASEP. There is a drive which is due to aggregation fragmentation models. That there is exactly. Okay, so then canonical ensemble. So yeah, I have just 5 minutes, so let me just summarize. So canonical ensemble, here the whole system, entire system is isolated, ergodic, which if it is ergodic, then postulate of equal a priori probability, all configurations are equally likely, and then I have the whole of the micron. So in the Yeah, so in the canonical ensemble, the situation that you consider is you are asking for the phase space distribution of a subpart, of a subsystem. Okay? This subsystem is a part of this bigger thing, and it is continuously exchanging like energy with the external one. And in the canonical ensemble, you look at the situation where you are allowed to exchange only energy and not particles. Okay. And then you ask what is the phase space distribution of this small part. So, that is given by e to the minus h of this small part. So, this is 1, let us say, and the important thing to note is that there is a t. So, this t is defined as the derivative of the entropy of the external part. It is the external part which is dictating the value of temperature that the small part is going to take, because the two systems will be in thermal equilibrium, and in thermal equilibrium this T is defined to be del S del E of this external one. And you can show that this also I discussed, that if I look at the energy fluctuation of this small part, it is a Gaussian peaked at a mean value, and the mean value is such that the two systems are at same temperature. Okay, and this allows you to make a connection between canonical and microcanonical. You say that I will choose my temperature T in such a way, temperature of the external world in such a way that the mean energy is peaked around the value which matches with the exact energy value of the microcanonical ensemble. Grand canonical exactly same, nothing else happens excepting that this small system is allowed to exchange both energy and number of particles, and then you have energy, you have number fluctuation, and that is set by the mu. Mu is defined to be the derivative of the free energy, the Helmholtz free energy of this bigger system with respect to the number of particles, and then it is the mu of the external system that tells me what is the average number of particles in this small part, and I will tune my mu such that the average number of particles in the grand canonical ensemble becomes the actual number in the canonical ensemble. Achha, regarding this thing, that let me, achha, this part is okay, right? I mean, I don't know, like you have to read, like it's not a, so you should, some of them came up to me and why you didn't cover Gibbs paradox. I mean, it's not possible, it's a one semester course. I mean, I cannot, see, my idea was to tell you the subtleties or the points which are not typically discussed in textbooks. I mean, calculations are pretty, I don't think in statistical mechanics you all need the expertise that, like even the expertise that you need to read dynamical system theory. I mean, it's pretty straight. Basically, you always have Gaussian, as far as I can tell. You have just Gaussian Taylor expansion, and that's it. To compute the partition function of a specific system is a different story altogether. But at least to understand this thing, there is not much. Achha, now the last thing that I talk about is this magnetic system, because there is always this confusion of which are the. Achha, one more thing is this, so maybe I also, this is also a confusion, that suppose the system has got 10 integrals of motion. How come in defining the microcanonical ensemble I have just the energy? What happened to the other integrals of motion? Maybe the total linear momentum is 0 and angular momentum is 5 or something. So, what happened to those? So, the way to look at it is the following, that while constructing the microcanonical ensemble, I am telling you that I am giving you a bucket of those microstates, all of which have got a fixed value of momentum, fixed value of angular momentum, all the constants of motion are the same, only the energy value is different between the different microstates, and I am telling you construct a collection of those microstates out of this collection for which the energy is the same. So, I am allowing only the energy to fluctuate between the different members of the microstate. While constructing, you may look at it differently. You may construct a different ensemble where you say that all the microstates that I am given to you have the same energy. Please construct a microstate for which the total momentum is equal to 0. Then I have to pick those. Okay? So, it is not that I am throwing away some information, it is the way in which I am constructing the. So, that brings me to this canonical ensemble for a magnetic system. See, for a magnetic system, in the canonical ensemble, what I will do is the following. I will say that look, I am giving you some particles, some spins or something. I am telling you that they all have the same magnetization M, whatever it is. And I am telling you that please construct an ensemble for me out of these microstates for which the energy is not constant. Like this energy is allowed to vary, but they all are given to be of the same magnetization value M. And therefore, the free energy that you get by taking log minus kBT log of the of the canonical partition function is a function of the given value of the magnetization, because that is how you have constructed your ensemble. So, magnetization is not a it is an independent variable, it is not a dependent variable. Magnetic field is the it is defined a posteriori, because you construct your ensemble and now you may ask what is the equivalent magnetic field that would give me this value of magnetization. So, this is one, but you can look at it differently, that I say that okay, I let magnetization to also fluctuate. You construct your ensemble, energy is fluctuating, the magnetization is fluctuating, but I say that the whole system is put in a magnetic field of 1 Tesla. So, now the magnetization is no longer an independent variable, it is the magnetic field which is the independent variable, and magnetization is obtained a posteriori. You do the calculation, you take the derivative with respect to the magnetic field, you get the magnetization. So, these things I think it is somewhat so in one case let me just write it. So, if fixed magnetization, you fix your magnetization, you tell me that look, I am giving you only those microstates that have got a given value of the magnetization. Now, you construct your ensemble by letting energy to fluctuate, and then the free energy that you would get will be a function of the magnetization. This is something that you are setting by hand. This is this initial condition, you are not letting it to fluctuate. So, also a function of the temperature of the external world in which the system, with which the system is in contact, and number of particles and so on. So, this will be minus kBT log of the canonical partition function, which will be a function of n and m and t. Okay, so, this is fixed magnetization. The other possibility is I say no, let magnetization take up any value it likes, but I have kept this system in a constant magnetic field of value h, and then this one will not be a function of m, but will be of h, and I know how to go from one to the other by, suppose I have this and I want to get rid of it and I want to bring in h. That is what I am doing, I am changing the physical situation. M is the independent variable, now I want to get rid of m, I want to bring in h. What does one have to do? Yeah, Legend? Legendre transform, probably, I do not know. So, the two are related by a Legendre transformation. So, I do not know, like every time Ustad says there is a French name, he looks at me, and so I said maybe I am obliged.
It's a general thing in the community, they all ask you for French.
Oh, is it? Oh, I am so honored to see. So, let me call it A n, and in my notation I think this is A n bar. So, this is bar just means that this is the ensemble that I got by considering h to be the h to be the independent variable. So, here it will be qn of ht, and the two will be related by a Legendre transformation. So, a n bar of h of t, that will be given by a n of h of m t, and the rule is that if I want to get rid of this, I want to bring in h. So, I do this, and did I do it right?
No, you want HM.
Sorry, HM, sorry. I want to get rid of m, and I want to have, then I have to derive with respect to m, sorry. And this one will be the h. So, one, the free energy in this ensemble is the free energy of the empty ensemble minus hm, and you can at once show that the internal energy will also be related like this. U bar is a function of h and t, u is a function of m and t, and by this transformation I am ensuring that u bar is a function of h and t and not of m and t. And there is a way to show it is, in one case you are including the energy of the source of the magnetic field, because u is what? U bar plus hm. Hm is the energy stored in your source, the magnetic field source. You know, right? Hm is the, so in one case it depends on which one you call the internal energy. Are you also including the source of the magnetic field into your description? Then it is one ensemble, or the other one is. Like again, this thing is always a confusion. For some reason they don't discuss. I don't know which is a good. I just learnt it by. Sorry, Callan. Okay, he. Yes, okay. The work done by a magnetic field in driving. By the way, so just typically you always use this. For example, in calculation of Ising magnetization in the Ising model, you will see that they put a magnetic field by hand. Like initially, they say this is H. I have kept the system in this magnetic field. You do the canonical partition function, you get this thing. And now you derive with respect to h, and then you get m. Because this calculation is difficult to do. You say you select those summing over those configurations that have got a given value of magnetization is difficult, and also physically this is not what you would do typically. That there is an external field that you are tuning. You do not care about magnetization. Let magnetization be determined a posteriori. I keep the system in a magnetic field, and then let it have the magnetization value that is allowed in equilibrium, which is the situation here. I keep it in a magnetic field H in contact with a thermal bath at temperature T with some number of particles, and then magnetization will be determined a posteriori. Well, this is kind of difficult to do experimentally. Okay, so I think that's what we did more or less. Okay, so thank you. Last lecture, yes.
So we may.
Okay, thank you very much. Thank you.
I think I got the proof of that square root of 5 minus a So any irrational can be written in a continuous fashion, right? You can write a plus b by c plus d by. So now you know that if you want a fast conversion, you want to make the denominators all denominators. Yeah. So as small as possible. So the smallest is 1. So if you put everything is 1, that's it.
Achha. That has the slowest convergence. Okay.
And that's this
That's this 1 by 1.
Square root of 5 minus 1 by 2.
1 by 1 plus, and that's square root of good enough. So that's basically.
What is the silver mean? There's also silver mean. There is, yeah.